Thank you, Davi, very much for the introduction, and thank you for the always very nice to be back at the Institute. So what I want to talk about today are, in fact, two results. And I want to talk about both of them because they're related, both in terms of technique. There's a certain technical tool in each of them, and also thematically. So both of them have different things to say about basically the variational structure of the Yang-Mills functional. So I should say at the outset, although I'll repeat this, this is joint with Casey Kelleher, who's here, and Jeff Streets. So I'm not a gauge theorist, so I view these more or less as some ideas in spectral geometry applied to gauge theory. But let me set up the picture here. So in a minute, I'll specialize to 4 dimensions, but at least at the outset, I have a closed Riemannian manifold. And I'm going to have a vector bundle E over X. So vector bundle. And then I assume that I have a connection. So we're given a connection, and I'm going to assume it's a metric compatible connection. So I have a metric as well in this vector bundle. Nabla. So this is going to map, sections of E across smooth vector fields to sections of E. And then I'm going to let F be the curvature of this connection. Then I can define the Yang-Mills functional. So which is just the L2 norm of the curvature for a given connection. So 1 of a connection is the L2 norm of the curvature. Okay, so what are critical points? We want to take a variation. So if we take a family of, so I have a connection, and I want to do a first variation. So I'm going to vary it by a one form that takes values in the bundle. So any variation can be written this way. So it'll be one form taking values in E. And then what I can do is take a first variation of the functional. Oops. And using the definition of the curvature and first variation, what you get is, I guess there's a factor of 2 here. And you get the inner product of the curvature of Nabla with the exterior derivative that's induced by the connection acting on this one form B. So if I have a critical point for the Yang-Mills functional, this is 0. For all such B. So if I just integrate by parts, we get the Yang-Mills equation, which says that the adjoint applied to the curvature is 0. So that's the Yang-Mills equation. And now, by virtue of being the curvature of a connection, we also have the second Bianchi identity, which I can write this way. So this is second Bianchi. Now, if E is just a trivial bundle, the manifold cross a real line, then in other words, F, you think about F just being a real value 2 or a real value 2 form. So if F is a real value 2 form in that case, a trivial bundle, then this would just be the equations telling you that you have a harmonic real value 2 form. Okay, so as I mentioned at the beginning, I want to eventually specialize to 4 dimensions, so let's go ahead and do it now. So for now on, always and forever, the dimension is 4. So there's several special features of 4 dimensions that I'm going to take advantage of. So let me go over those. Some are obvious, some less so. The first one is conformal invariance of the functional. So if I conformally change the metric, you can just track through how things scale in the functional, and in 4 dimensions, it's scale invariant. So in particular, if G tilde is, say, E2W times G, then then the energy, oops, the Yang-Mills energy, excuse me, doesn't change. Write it this way. Well, I'm mixing metrics here, but anyway. Okay, so now less. So another feature of 4 dimensions is that we need to exploit is self-duality. So the bundle of 2 forms in 4 dimensions will split. So assume not only that X is 4-dimensional, smooth, closed, but also let's assume it's oriented. So I can split the bundle of 2 forms into self-dual and anti-self-dual 2 forms. So let's see, self-dual and anti-self-dual. So correspondingly, the curvature of the connection will split in this case, in the self-dual, anti-self-dual part. So so we've got the first variation calculation of the Yang-Mills function, the Yang-Mills equation here. It turns out that if one of these pieces vanishes, that automatically satisfies the Yang-Mills equation. So the basic idea is that, well, let me record this now. So just using Hodge theory, so the adjoint operator shows up in the first variation. All right, and then depending upon your conventions, your sign conventions and everything, there might be a plus or minus here. But anyway, you can rewrite the adjoint in terms of the actually exterior derivative and then conjugated by the star operator. This leads to the following definition. So a connection is self-dual or anti-self-dual if the curvature is self-dual or anti-self-dual. So i.e., if, let's see if I get this right. So self-dual if the minus part vanishes, and anti-self-dual means the plus part vanishes. Okay. And then you can check using this formula that if, so maybe put it over here. I need to write it a little bit smaller maybe. So if nabla is self-dual or anti-self-dual, then nabla is a Yang-Mills connection. It satisfies the Yang-Mills equation. All right, so you just check this by using the second Bianchi plus this expression for the adjoint. All right, so it's a critical point, but actually you can say more. But to do that, you need to consider some topological invariants. So that namely introduce the Chern classes. So the second Chern class, the bundle, is given by, and again, this depends upon your conventions, but for me, I guess it's going to be minus 1 over 8 pi squared. And the form you integrate after you simplify turns out just to be the difference squared of the self-dual and anti-self-dual part of the curvature. So this tells us very quickly that, in fact, not only are self-dual or anti-self-dual connections critical points, but actually they have to be global minimizers. Right. So you can rewrite the Yang-Mills energy in terms of the second Chern class in the following way. So the Yang-Mills of connection is plus or minus 8 pi squared second Chern class, and then plus 2 and the self-dual or anti-self-dual part of the curvature, just by splitting the curvature and then using the formula for C2. Well, if you want to think about it as an SU2 bundle, that's fine. I mean, I don't really care. So the point is we get a lower bound of this form. And I want to highlight this and hopefully not erase it because I'm going to come back to this later on. So the corollary is that so nabla is self-dual. So if nabla is self-dual or anti-self-dual, then nabla is a global minimizer. of the Yang-Mills functional. Oh, yeah, so I should say, whether it's self-dual or anti-self-dual, in either case, the term used collectively is instantons. Right. So instanton solutions are of fundamental importance in the applications of gauge theory to four-dimensional topology. But that's a very different story from what I want to talk about today. So let me begin to talk, explain what I have in mind. So as I mentioned at the beginning, this is really a talk about some variational properties of the Yang-Mills functional. So the first kind of results I want to talk about are so-called gap results. So let me phrase it this way. So same setup, a vector bundle over a four manifold. And now let's suppose I have a Yang-Mills connection. So here's the kind of question I want to ask. All right, so one kind of, if it's a Yang-Mills connection, it could be an instanton. So maybe it's, let's say, self-dual. Well, actually, the way I'm going to write it, I guess, is anti-self-dual. So it could be anti-self-dual. So the plus part of the curvature vanishes. So that's one possibility. But suppose that's not the case. So this is not identically zero. Then is there necessarily some discrete gap in the Yang-Mills energy? Right. So a little more precisely, does there exist a number delta, which is certainly going to depend upon the bundle, such that once the self-dual part of the curvature is small enough, then actually we have to have an instanton, so it has to be self-dual. So either this, for a Yang-Mills connection, either it's self-dual, excuse me, anti-self-dual the way I'm writing it here, or it has to be above this energy level. Okay, so there's a number of results along this line in the literature. Let me hit on a few here. Actually, the first one I want to hit on is not exactly in this kind of vein, but it's nevertheless important. So let's do to Bochner and Lawson back in 81. Okay, and so this is, I guess, this is over the sphere. In fact. So the result is following. So here I'm doing things in terms of the L2 size of the self-dual part, but they did it in terms of the L infinity size. But anyway, it's the same kind of spirit. So it turns out they have a number which is 3, and they say if the L infinity norm is less than 3, again for a Yang-Mills connection, right? Then you have to be ASD. Okay. 3. Yeah, 3. So it's later on I'll write down a Bochner formula, and when I write that Bochner formula down and you specialize the case of the sphere, it's a competition of two terms, and you just realize if this hypothesis holds, the positive term beats the negative term. That's what it boils down to. Okay, but in the direction of L2 results. No, I guess it's sort of, I'd have to think about what you mean by sharp. Because in a small set, are you allowing it to be a little bit bigger than 3? Or yeah. I know where the 3 comes from, and there are examples where, okay, so there's a standard solution on the force sphere, the BPST instant, where you will have identically equal to 3. All right, so in that sense, I guess you say it's sharp. But anyway, I want to concentrate on the L2 statement. Okay.
That actually doesn't depend on E. It could be any vector over E.
Here, yeah. Well, yeah. I think because of the algebra, it doesn't matter for this one. Yeah, because it's from a Bochner formula. So.
Well, in all honesty, Bochner-Weissenbach block usually has a curvature term from the bundle and one from the manifold over which it sits.
Right. So this is S4, and that's what's feeding into the 3.
Right, but there may be a curvature term from the bundle, which may.
That's what this is.
Oh, that's where it only shows up there.
Yeah.
Because of the Bochner.
Yeah.
All right,
Yeah. Yeah.
That's the only
Yep.
way it shows up.
Yeah.
The first palette.
Yeah, exactly. Yeah. Okay, so but in the L2 direction, it's two results about at the same time. So Minnow, I guess this is 82, and Parker. I'm going to group these together, different papers, but I'm going to group them together because they're very similar in spirit. So the answer is yes, there is such a delta. And okay, what does the delta depend on? It's not explicit. And what does it depend on? So I'm going to be a little bit vague here because eventually I'm going to write down this Bochner formula anyway, and then it'll be easier to be more precise about what everything depends on. But so the volume of the manifold, and then there's some condition on the curvature of the metric of the manifold, which it's a kind of positivity condition. I'll come back to this later. And then some kind of dependence upon a Sobolev constant. And then, of course, the vector bundle. And the basic idea here is, so for this result, as I said, it's a pointwise Bochner argument. For this result, you use the Bochner argument, and then you want to do kind of an epsilon regularity, and that's why there's a Sobolev constant dependence here. Right, so it's really epsilon regularity in disguise. So it just says if you have L2 smallness and you beat the Sobolev constant, the only solution is 0 is what it boils down to. And then more recently is Feehan. So this would be 2016. So here, so again, the dependence is kind of complicated. But so Feehan, he drops this positivity condition, and he replaces it with a kind of genericity condition of the metric. So he defines what he means by a good metric, and he shows this is a generic property. And then, so there is such a constant, but it depends upon the metric sort of in a non-obvious way, and then the bundle. But nevertheless, dropping this positivity condition that I'll eventually talk about is actually kind of crucial because this actually has topological implications. So this is a more general result. But in both these cases, I guess you don't really, you could probably estimate delta, but you don't really have a concrete number. Okay, so let me state the first result I want to discuss. I'll call it theorem A. Again, this is Keller and Streets. So it basically says that yes, there's a delta, and we can quantify it, and it's more or less sharp, or at least sharp in certain important cases. So same setup, but we also make a curvature assumption that I'll get to in just a second. So closed, oriented. So nabla is a Yang-Mills connection. Okay, so then the result is the following. I'll state it and I'll have to explain the notation. So then nabla is an instaton. Well, let me put it, I'm going to do it for the self-dual part. So then the connection is anti-self-dual, or you get the following inequality. So it says the following. Our result only holds if the scalar curvature of the base manifold is positive. And we measure that in a conformally invariant way by looking at the Yamabe invariant. So this is the Yamabe invariant. And this is less than or equal to, so I got to get the constants correct here. So 3 gamma 1 of E, I'll explain in a second. The L2 norm of the self-dual part of the curvature, plus 2 root 6 the L2 norm of the self-dual part of the Weil tensor. Now, what is this gamma 1? So it's a constant that you can compute, and it depends upon the bundle. But there is a universal upper bound. So where gamma 1 depends upon the bundle, but the universal upper bound, it's always less than or equal to 4 root 3 over 3, depending upon your conventions. So in particular, for example, if you're on the sphere, all right, then this is explicit number. All right, this is just the volume of the sphere. Well, what is the volume? The square root of the volume of the sphere times the scalar curvature of the sphere. So anyway, this is explicit on the force sphere. You can get an upper bound on this constant, and then of course the sphere is conformally flat, so the Weyl tensor vanishes, so this term's not there, and so you get a lower bound. So generally you get a lower bound whenever this term is bigger than this term. But if you apply it to the sphere, let me just mention that, and I bet I erased it. I didn't. Hooray. Okay. So the corollary is that if you're looking at a bundle over this force sphere, and then let me, so that we can pin down a value of gamma 1, let's say an SU2 bundle, just because we know the explicit constant here. And again, nabla is the Yang-Mills connection. Then either it's anti-self dual, or this estimate written out tells you that the Yang-Mills energy is greater than or equal to 8 pi squared times the absolute value of the second Chern class plus 16 pi squared. So compare that with this general inequality here. Right? So this is the same as this, right? So it says that, all right, if you're not an instanton, if you're not anti-self dual, then the gap here is 16 pi squared. And that 16 pi squared is there are examples where you hit that value. This is full. This is full, yeah. That's why you bring in the second Chern class. Yeah, it's full. All right. So there's two. This is loud. So there's two ingredients in the proof, and I'll postpone both of them to the second hour. Well, the second part of the talk, I promise they won't both be 1 hour. So the key ingredients. So the first one is, I guess I should have said this when I first wrote down the formula. So one, a little bit unsatisfying things about previous results, just in addition to the fact that you couldn't really quantify these constants, is that it doesn't really reflect the conformal invariance of the Yang-Mills energy. So all the data here is kind of sensitive to conformally changing the metric, but the Yang-Mills energy is insensitive to conformal change in the metric. So in this estimate here is conformally invariant. Every term is. Okay. So and that's crucial for us, and we exploit that in the proof in a key way. So what we want to do is not, if you give us a base metric, we don't want to necessarily use that to do our estimates. And in particular, when we write down the Bochner formula, we do not want to write down the Bochner formula with respect to the given metric. We want to first conformally change it to a more optimal metric. So it's a choice of conformal representative. That's really the only and new idea. And then the second key thing is this Bochner formula that I keep referring to, which is well known. So it's just applying this idea to the Bochner formula. And I'll write down the Bochner formula in the second part. Okay, so that's the first thing I want to talk about. All right. And then the second thing I want to talk about are index estimates. Okay, so this first result says you're either at the minimum energy or you have some fixed gap above that. So if I have a non-minimizing solution, so I'm above that energy cutoff, then the next question is, okay, what can I say about the variational structure for those solutions? Right? They're not minimizers. So you want to look at the second variation and look at the index. So you could have directions where the Yang-Mills direction, the second order where the Yang-Mills energy could decrease and increase. So that's the theme of the second. Okay, so the setup now is we always have as before Young's connection. And now we want to do a variation to second order. So take the same kind of variation we talked about before, but take the second one. Oops. Okay, what do you get? Well, I guess the way I'm going to normalize this is a factor of 2 here. You get an index form. So what happens is some operator, I'll call J for Jacobi, that acts upon B, and you take the inner product with B. All right, so what is this operator? So this operator is the following. It's in terms of the rough Laplacian. I should say, by the way, my Laplacian on Euclidean space is this, okay, just to make it clear on the signs and everything. So it's minus the rough Laplacian. And then there's another second order term. So basically what's going on here is this is just going to be the Hodge Laplacian. Right. So it's another second order term. And then a term involving the curvature of the bundle. So I'll write it this way, and I'll say something in just a minute about this. And then a term involving the curvature of the base. Okay, so I'm using a lot of abbreviations here. So the bracket operation can be extended to a bracket operation on bundle valued 1 forms, and then 2 forms. It can be extended to a bracket operation on 2 forms with a 1 form. So this bracket here will map 2 forms cross 1 form to 1 form. Let me not write it out because there'll be a boatload of indices and it won't tell you anything that you need to know for this proof anyway. And then the Ricci is a symmetric 2 tensor, and then there's an obvious way in which any symmetric 2 tensor acting on the tangent bundle of the base can be extended to an action on 1 forms, bundle valued 1 forms. So we can just view this Ricci as an endomorphism. This. Okay, so due to gauge invariance, we can actually assume that the second term vanishes. So this is a choice of gauge that's always possible. Yeah, exactly. Yeah, exactly. So I'll put gauge. So without loss of generality, we can assume that that the divergence of B is 0. So that term's gone. So then we can just look at the Jacobi operator. I flipped my boards here, sorry. Oops. Just leave it here. Okay. So from now on, we're just going to look at the operator without the second term. And we have, so the bracket, I'll write it this way, and then plus Ricci. So there's our operator. Okay, so now with this gauge fixing, we can now view this as an operator. So it's a differential operator on 1 forms. It turns out so the leading term is the rough Laplacian after we've done the gauge choice. So it's elliptic and it's self-adjoint. So let's label the eigenvalues. And because the leading term is minus Laplacian with minus signing conventions, the eigenvalues march off to infinity. So let me label them without multiplicity. Okay. So I can label the eigenspaces. So E lambda 1, E lambda 2, et cetera, et cetera. Okay, so the index is just going to be the number of negative eigenvalues, the dimension of the sum of the dimensions of all the eigenspaces associated to negative eigenvalues. So we have the index. So that's denoted I of nabla. So that is going to be the dimension. So I'm going to just take the union of all the eigenspaces associated to negative eigenvalues, and then the nullity. So that'll be denoted by nu. So that's just the dimension of E0. So if you have a kernel. So what do we want to do now? So for arbitrary, okay, so actually when I state the eventual result, we're going to, as part of the assumption, we're going to assume we're not an instanton, so we're not a minimizer. So we're looking at higher energy solutions. And what we'd like to do is get an index bound. So the rough idea is that if the index is large, all right, then the energy should be large. Or, same result just stated in a different way, that if you have a bound on energy, then the index cannot be too large. Okay, so if you have, if the index is 0, then we say that the connection is stable. So that means the second variation is non-negative. Okay, so let me give a little overview of what's known in this case. So again, let me begin with a result of Bourguignon and Lawson that really isn't quite in the spirit of what I'm after, but nevertheless, it's an important result. That paper was filled with really fundamental results, in fact. So again, oops. Same paper. Okay, so this is again for bundles over S4, and here the Lie groups are fixed. So this applies to SU2, SU3, and U2 bundle. And it says that stability implies instanton. So this is an extremely strong kind of statement where, okay, if I know something about the index, then I know something about the variational property of the solution. I mean, it can't get much stronger than this. Okay, but much more in the spirit of what I want to talk about, where you estimate the index, is a result of Urakawa. And this is in 86. So there's a number of assumptions here on the base manifold. So first, the assumption is that the Ricci tensor is bigger than k times the metric, where k is positive. So you have to positive Ricci curvature for the base. Then the estimate, so it's an estimate for the index plus the nullity. So they're bounded by a constant. And the constant depends upon the lower bound on the Ricci curvature, a pointwise norm on the curvature of your Yang-Mills connection, the dimension of the manifold, and the bundle. Okay, so this is in the spirit of what we want to do, but once again, I guess I should say, it's not obvious at all. Well, I guess it follows from the invariance of the functional, but it takes a little bit more work than that. But in any case, note that the index plus nullity is a conformally invariant. So once again, the estimate you have here doesn't capture that conformal invariance. You also have the strong assumption on the base manifold. All right. And we want to get rid of that. Well, as much as we can. So like in the first result, we're going to have to assume positive scalar curvature again. Okay, so let me state what we were able to do in this case. So I'll call this theorem B. Same, different paper, but all three of us. Okay, so again, a vector bundle over or a 4-manifold, and now actually the structure group comes into play. So in a sort of mild way, but it does come into play. Okay, so the statement is that, and so nabla is a Yang-Mills connection. Okay, so then nabla is an instanton. So this is a, let me state this a little bit more carefully here. So it's an alternative, okay? So either nabla is an instanton, or you get an index plus nullity estimate. And so the estimate is a bit strange looking, but I'll explain why it's strange looking. It's not our fault. It's the technique, so I guess it is our fault. But so you get a strange constant 144 e squared times the dimension of the group divided by, okay, once again, so Urakawa's result assumes positive Ricci. We're able to soften that to positive scalar. And then again, the Yamabe invariant appears. So times the square of the Yamabe invariant times, okay, I should have shifted this over here because there's a big kind of strange expression. So we want the energy to appear. It does. So it's 12 times the Yang-Mills energy. And there's other terms that are conformal invariants. And so once again, the Weyl curvature comes in, just like it did in the first result. So we get 3 times the norm squared of the Weyl tensor. And then there's a strange cross term that comes in that looks like the following. So it's 3 root 2, the norm of the Weyl tensor times the norm of the curvature. When I explain the technique, you'll understand why you get kind of strange constants in this cross term here. And then a topological term, so minus 12 pi squared times the Euler characteristic of the manifold X, the base manifold. So again, everything in sight is conformally invariant. And this tells you that if you have large index plus nullity, then you must have large energy. At 2.718, I can't, yeah. No, it's, so I will tell you, in fact, let me write down a corollary. Let me make a couple remarks about where this result comes from, and of course I'll. Well, okay, so you make that assumption when you write down the operator, right? So this is estimated here you're estimating the number of eigenvalues of this operator, and that operator is elliptic because you made the Coulomb gauge choice. Okay, so once again, in the case of the sphere, many of the constants are more explicit, and certain terms drop, and it's a cleaner statement. So now, if you're over S4, so if nabla is not an instanton, so the second alternative, then the index plus the nullity is less than or equal. So now the constant is 9e squared, the dimension of the group, and then times -1 plus 1 over 8 pi squared E moles energy. So the constants are a little less foreboding. Okay, so what? Yeah, so I understand your question. Where did E come from? Why did that come in? What's going on here is you're estimating the number of negative eigenvalues, and what both proofs use at their core is looking at the trace of some the trace of the heat kernel for some operator. So you look at so you're looking at the trace of the heat kernel, and this is why you end up seeing an exponential function. That's exactly where it comes from. Okay, and so in fact, more of that's also why the Ricci curvature, positive Ricci curvature assumption is necessary in Urakawa's method. So he also has to do some heat kernel comparison theorem, and that comparison theorem holds for positive Ricci curvature. So again, for more or less for reasons of spectral theory, you need to make that curvature assumption. So we bypass that and are able to get by with, again, just positivity of the scalar curvature. Now let me see where I am. Okay, so maybe what I'll do is, yeah, okay. Just trying to figure out how far to go. Okay, let me just tell you the two ingredients. So for the first theorem, so really the proof boils down to this well-known Bochner formula, and then carefully exploiting the conformal invariance. That is also used in the proof of this result. So again, choice of conformal representative plays a role. And this choice is, in some sense, based on the choice in the proof of theorem A, but you need something more. Okay, so I mentioned there's something about the estimating the trace of the heat kernel. So what we need is I'll abbreviate it, the CLR estimate, and I'm going to spend some time talking about that in the second half. So this has to do with estimating the number of non-positive eigenvalues of a Schrodinger operator. So in fact, this is mostly what I want to talk about in the second half. So, but with the last few minutes, because it doesn't take too long to explain this, let me, and it appears in both results, let me talk about this choice of conformal representative. Because the idea is very simple. Okay, so this is an idea that all times the idea is to take the Yamabe problem, well-known Yamabe problem, and modify it. So let me explain. So suppose I have two metrics that are conformal to one another, and then because I'm going to talk about the scalar curvature, there's a good way of writing the relationship, the conformal relationship between them to make the formulas turn out nicely. So everything I'm going to do here is eventually going to be in dimension 4, but for the time being, what I'm going to say now just depends upon the dimension being at least 3. So suppose I have a metric and I conformally change it, write my conformal factor this way to a new metric g tilde, then there's this well-known formula that the scalar curvature of this metric is related to the scalar curvature of this metric via some elliptic operator acting on u. And the form that operator takes is you have some negative power of u here. It shows up. And then you have a differential operator. Well, I'll write it as, I'll call it LGU. So LGU, this is called the Yamabe operator or the conformal Laplacian. So it's the Laplace operator. There's a dimensional constant here that just pops out of the formula. So times the Laplace operator, and there's the term involving the scalar curvature of the initial metric here, g. Okay, so let's let lambda 1 about g be the first eigenvalue. Now, this operator has the nice property that it's conformally invariant. So if I conformally change the metric, then So the invariance property here, it goes like this, that, what is it? I do feed the 4 over n minus 2. G applied to u is feed the minus n plus 2 over n minus 2 LG VU. All right. So it's invariant in this sense. So with these weights. So, but it follows, you can just check that the sign of the first eigenvalue is conformally invariant. All right, and then it's the same sign as the Yamabe constant. Okay, so now what I want to do is I just want to take the scalar curvature that has this nice transformation law and an associated nice operator and add some 0th order terms to it. So instead of just looking at the scalar curvature, I want to look at things that scale the same way but have simpler conformal transformation laws. So for example, if I look at the norm of the Weyl tensor, let's only write it this way. So if I conformally change the metric, just like I described before, and I look at the corresponding, look at the norm of the Weyl tensor of G tilde, then you'll just have a factor of, what is it, minus 4 over n minus 2 times the norm of the Weyl tensor with respect to G. And then suppose I measure the norm of this. How do I write this? The curvature 2 form. Oops. Then I'll get this. All right, so these transform in a very simple way. So what I can do is just modify. This is the origin of this term, modified Yamabe problem. I can just look at sort of modified scalar curvature, which is just the scalar curvature, and then minus any multiply I like of the norm of the Weyl tensor and norm of the curvature of any given connection you like. And then if I check how this changes under a conformal transformation, so if G tilde is u to the 4 over n minus 2, then just combining all the formulas I've written down, what you get is that this transforms in the same exact way as the scalar curvature. You just have to modify the operator appropriately. So if you compare with the formula over there for how the scalar curvature changes, I put the same power here, and I'll put an operator. Let me do it script L. And what is script L? So script L is the principal part is the same. So it's minus 4 n minus 1 n minus 2 Laplace. Plus scalar curvature, and then minus this term here. All right. So you can add these weights that scale in a simple way under conformal transformation, and it behaves as if you're just looking at the scalar curvature. Okay, so and because of that conformal transformation law, the same fact holds. So the sign of the first eigenvalue of this operator is conformally invariant. The sign of this script L is also conformally invariant. So, excuse me, of lambda 1 of script L is conformally invariant. So you get this easy fact. Right. So if you're given any conformal class of metrics on a compact manifold of dimensions at least 3, then there always exists a conformal metric. So given any conformal class, you can pick out a metric in that conformal class such that this curvature, this modified scalar curvature I just defined there, has fixed sign. So it's either strictly positive on the manifold, identically 0 on the manifold, or negative on that manifold. All right, and which case just depends upon the sign of lambda 1. Okay. And this is what we're going to use in the proof of both of them, is that we're going to take, you'll see a scalar curvature term in some formula, a Bochner formula or an index form. You'll see a scalar curvature term. We're going to modify that scalar curvature by throwing in terms that scale in a simple way. And we'll collectively look at this modified scalar curvature. We'll use the fact that in any conformal class, we can fix the sign of those terms. This, and this, and then we have to sort of analyze which case we're in. Okay. One minor point, it's a bit of a headache. So look, I've taken the norm of things. So in general, that's going to be Lipschitz. So by elliptic regularity, when you prove this might just be a C2 alpha metric. All right. Okay, but then you can just sort of smooth things out, and this case and this case is okay, but here you have to be a little bit careful, right? But then, so what you have to do is you have to regularize throughout and take limits. It all works out, but it's a headache that I won't bother mentioning again. Okay, well let me stop here, and I'll pick up with the Bochner formula after the break. All right, so I erased that lemma, so I rewrote it over here. So we'll need this eventually, so I'll try to avoid using that board. Okay, so I'd mentioned for the first result that it's really just an application of this idea about modifying the scalar curvature and then looking at a certain Bochner formula. So let me tell you what that Bochner formula is. So again, this applies for Yang-Mills connection. And it says the following. So so I don't have to keep referring to the connection. So let me just write F plus instead of F nabla plus. Too many subscripts and superscripts. So it says the following. If I have the Laplacian of the norm squared of the self-dual part of the curvature is equal to the norm squared of the covariant derivative. And then now, Penny mentioned this, there's a term involving the curvature of the bundle. And it shows up as a bracket. So now the bracket gets extended to two forms. Right? So this bracket operations on two forms. It results in a two form, which you then take the inner product of this two form. And then, then there's terms which depend upon the curvature of the base manifold. So I'll write in kind of again, to make this explicit, it would take a while, and this is good enough for explaining what's going on here. Let me write this. All right, if in the trivial case you have a real value 2 form, then there's no bundle curvature there, and then this is the Bochner formula for harmonic 2 forms on a 4 manifold. Okay, so back to the bundle setting, what's going on here? So you have this term involving the bundle curvature. Now, when I was mentioning these gap results of Minnow and Parker, I said there's a certain positivity condition. So basically, they want to assume some condition between the self-dual part of the Weyl tensor and the scalar curvature. What they want to basically do is throw out the second line here, okay? So that really it's just this term and this term on the right-hand side. That's the basic idea. And then for the Bourguignon-Lawson, for the sphere, this term's gone. You just plug in the scalar curvature of the sphere, and it's just a competition between these two terms. That's where that's coming from. Okay, so we want to use this, but we want to use it. We want to, first of all, estimate these terms in as sharp a manner as possible. And then there's one sort of, well, at first it seems kind of remarkable, but then you realize it sort of has to be there. But let me explain. So, claim, or it's a series of claims. It's basically estimating these terms. So first of all, what order should I do? Let me do it order over here. So if you look at the bracket term, so in absolute value, well, let me write it this way. So it appears with a minus sign. If I claim that's greater than or equal to minus this constant gamma 1. In fact, you could take this as your definition of gamma 1. So it's just some algebraic constant. All right, depends upon the bundle. And then if you go through the linear algebra, you can see exactly what I wrote before, that it has universal bound depending upon this. Okay, it's again just a linear algebra exercise, so this is nothing big. And then there's the Weyl term. So it turns out that this really boils down to when you take apart the action on these bundle valued 2 forms, it really just sort of boils down to the estimate in the real valued case. And the estimate you get is the same estimate you get in the real valued case. So it's 2 root 6, or wait, hold on, I have to divide that by something. Sorry. It's root 6 over 3, excuse me. The norm of the self-dual part of the Weil tensor times the norm squared of f plus, and this inequality is sharp. So this is 2. And then the other part, yes, is so this is more involved. And again, this is something that is known in the real valued case. It's actually due to Walter Seaman. But it holds in the bundle valued case. If you have a Yang-Mills connection, it says that the norm squared of the covariant derivative of the self-dual part is greater than or equal to 3/2 the gradient of the norm of f squared. And this 3/2 is sharp, and it's absolutely crucial for the argument. If it were worse than that, none of this would work. Well, at least our approach wouldn't work. But it sort of has to be because of conformal invariance, it turns out. OK, so if you put it all together, so 1, 2, 3, plug it into the Bochner formula, what do you get? So you get the following. Well, actually, all right, so I don't want to skip steps. I'll skip steps. So I estimate each one of these terms using the formulas or the inequalities above. I can't do anything with this term. It's as simple as you're going to get it. But here's the deal. When I estimate this via the Kato inequality, I still have a term over here that involves the derivative of the norm. So what I want to do is basically to get rid of that positive term so I can absorb it and it can help me, is I look at the Laplacian of a different power, right? And then this disappears. And the magical power turns out to be precisely 1/2. Okay? So that makes that term go away. And then you have an inequality. So you can think of the following as holding away from the 0 locus of f plus, or in a sense of distributions, however you like. And then when you get over here, and this is sort of the magic, with this choice of power that's driven by the sharp constant in the Kato inequality, combined with the fact that you have a 1/3 here, so they're all interplaying together, and you get a 1/6. And that's going to be crucial. So, and I'll just collect all the terms under this 1/6. So it's r minus 2 root 6 norm w plus minus 3 gamma 1 norm of f plus times that power of f plus. So it's exactly this 1/6 coefficient that shows up in the formula for the conformal Laplacian and also the modified version. So you recall this. So if we take phi to be, so my modified scalar curvature I want to study for this problem is, so I had the general statement over there. Instead of looking at the Weil curvature and the curvature of the Yang-Mills connection, I'll just look at the self-dual parts. And I'll take my first constant to be 2 root 6, and I'll take my second constant just to be 3 gamma 1. So this is my modification of the scalar curvature. So I just collectively call this phi. And then what's the conformal transformation law for that? That was that operator script L. So in 4 dimensions, that's minus 6 Laplacian plus phi. So this was the operator whose first eigenvalue, such that the sign of the first eigenvalue is a conformal invariant. And that's exactly the operator looking at here. So in fact, I can rewrite this big long inequality here very compactly as 0 is greater than or equal to L applied to f to the 1/2 power. So this immediately says that the first eigenvalue of this operator is less than or equal to 0. Okay, so what I want to do now is just apply the lemma. Okay, so I apply the lemma. I get a conformal metric so that the corresponding curvature quantity, this one here, has a fixed sign. It's either identically 0, because it's less than or equal to 0. So it's either identically 0 or it's strictly negative. Okay? All right, so I'm done with this. So the lemma over on the other board implies that there exists a conformal metric such that this okay, so let me write it this way. So this modified scalar curvature is less than or equal to 0. So I write that out, and that's this. Let me put the other terms on the other side. Plus 3 gamma 1. I get this. All right, then you're done. You just integrate both sides. So if I integrate both sides with respect to the volume, so this is bigger than equal to the Amabi invariant times the power of the volume, namely the square root of the volume. Right? Use Cauchy-Schwarz. In each case, I get a factor of square root of the volume, which I just cancel out. Okay? So on the left-hand side, you end up with the Amabi invariant of your manifold. Over here, I get 2 root 6 L2 norm of Weil, and then 3 gamma 1 L2 norm of L plus. So that proves theorem A. All right, so now the proof of theorem.
The estimate of this first thing is gamma 1 of E sharp or accurate?
Right. So it depends upon the bundle. So if you ask if it's sharp, so the way to say it is, by definition, it's you take omega any 2 form, bundle value 2 form, and you look at the inner product of omega with omega bracketed with itself, and you divide by omega cubed. So gamma 1, by definition, is the soup over all omega. So that's just the definition.
Omega self-dual.
Yeah, that's just the definition. So then using some algebra, you can see that there's this universal upper bound. But you might have bundles for which this is small. In fact, you can write down bundles for which it's smaller. Yeah. OK, so now on to what I do with the index estimate. OK, so here the story. I can do it here. Here the story kind of changes because now we have to a little more background on this idea from spectral theory. Okay, so what we're doing is we're taking this Jacobi operator that comes from the second variation, and we're reviewing it as a kind of Schrodinger operator, of course, acting on sections of a bundle. Well, we're trying to estimate the number of negative eigenvalues. Well, this is a very if you replace the bundle setting with, say, domains in Euclidean space, this is a very classical kind of question that comes up in mathematical physics. So, in fact, this is, I'll refer to it as the CLR estimate, or inequality. So who are C, L, and R? So do you know how to pronounce? Sweeco. Thank you. So I guess this is the dates. If I get this correct, it's 1977, and then Rosenblum, I guess like 76. So these are independent and very different proofs, in fact. So it's a case of 2 of them working, I guess, in the West at the same time with independent proofs, and then someone working in the East. So here's the statement. It's a really beautiful result. So it says the following, that so consider a Schrodinger operator of the form minus Laplacian plus V, and let omega be a domain in Euclidean space. at least dimension 3 bounded. So we're going to look at the Dirichlet eigenvalues of this operator. We want to look at the counting function that counts the number of non-positive eigenvalues. So N0s is the number of eigenvalues of S that are less than or equal to 0. And the CLR result is that this can be estimated by some constant, dimensional constant, times the ln over 2 norm of the negative part, so let me write this way, the negative part of the potential V. Okay, so as I said, these proofs are quite different, and as we spent a fair amount of time trying to see if there was any way to try to adapt them to our setting, where you have this this operator on this bundle, on this vector bundle, and we couldn't see how to do it, which is it's still a very interesting question. But in any case, it turns out there was another proof of this result appeared a few years later, and that was much more adaptable. So this was due to Li and Yao in 1983, and they gave an explicit constant of the following form. Well, it doesn't really matter. I can write it down, but it won't really figure so much. And well, it'll partly explain where our constants come from. So this was their constant. So in fact, the E in our constant really comes from this E in the Li-Yao. And again, it basically boils down to a trace of some heat kernel. So, and it turns out that the great thing about Li-Yao's estimate is that it immediately adapts to manifolds where, and in their argument, quickly adapts to manifolds where you're looking at, say, a closed manifold and you drop the boundary condition. Right? So in that case, if you apply it in a compact manifold, then if you trace through, you see that they're constant in their inequality now. It depends, of course, on the dimension. But how does it depend upon the metric? And it concretely depends upon the Sobolev inequality. So basically, if you have Sobolev constant control, then their argument runs. OK, so I won't have time to take you through the proof of Li-Yao, although it's fairly, it's fairly straightforward, but it's a little bit long. But each step is very natural and nice. So let me just tell you how we apply it. So we take their proof, but we also need an additional estimate, and we're able to put it into a vector bundle setting. And so our general result, so I'm going to state this in 4 dimensions. You can do something more generally, but it's not quite as nice. Let me just state it in 4 dimensions. And so nabla is a connection. So this is some metric compatible connection. We're out of the Yang-Mills setting. I just want to be able to define a rough Laplacian so I can define a Schrodinger operator. That's all that's going on here. And so if I have that connection, I can define a Schrodinger operator. So, but I want to look at a very special kind of Schrodinger operator. I want one that looks like to leading term. So this is acting on sections of the bundle. But I want the leading term to basically look like the conformal Laplacian, same coefficient here, and then maybe minus a potential. So it's acting on sections of your vector bundle. And I assume that V is non-negative. All right, then it's just a matter of running through. So we use the Li-Yao proof, but there's a key point where, so their proof is for the Laplacian acting on functions. We need it for operators acting on sections of vector bundle. And there comes a point where you have to say that there's some comparison between traces of heat kernels of rough Laplacians on sections of the bundle versus the Laplacian acting on functions, right? So for that inequality, so there's actually a number of results in that line, but we had used an argument of Lee and Donnelly, or Donnelly and Lee. In any case, putting it all together, what you get is the following estimate, that if the Amabi invariant of your base is positive, then you can estimate the number of negative eigenvalues of your Schrodinger type operator here by 36e squared divided by the square of the Amabi invariant, so that's where that comes from, and then times the rank of the bundle, and then times the L2 norm of V. I guess it's L2 norm squared, sorry. Okay, so even knowing that, actually, it's not a plug and play kind of result. You cannot just take the operator that you get from the second variation, the Jacobi operator from the second variation of the Yang-Mills functional, plug it into this, and get any kind of estimate, get an estimate that even resembles what we did. So I need to spend a few minutes to explain how you get from that to our conformally invariant estimate. Keep that up there. All right. So let me. Oh, and I should also say, I don't. If I have time, what I'd like to do is. So now what I do is I want to take this estimate. I do want to apply it to the Jacobi operator for the Yang-Mills functional, but after we do a conformal change of metric that's in the same spirit of what we talked about for the proof of theorem A, and then show how eventually this index estimate of ours pops out. But I also want to show that this can be applied to prove other kinds of index estimates. So at the end, if I have time, I'll try to quickly show how this can be used to estimate the index of Einstein metrics, which is a different kind of problem, but turns out the Jacobi operator has some similar structures. Okay, so now what I want to do is a sketch of proof. So theorem B. All right. So how does it go? All right. So step one. We're going to, again, do a conformal change of metric, and it's very similar to what we did before. So now I want to kind of tweak the curvature a little bit. So remember the operator we looked at was some modification of the scalar curvature, and I had 2 root 6 W plus here, and then 3 gamma 1, norm of the curvature there. All right. So I want to drop the pluses, because it turns out that the Jacobi operator, you can't detect the self-dual part or the anti-self-dual part. So let me drop those. Right? And then I want to put a parameter t here, and I want to think about t being between 0 and 1. Okay. So I'm looking at a whole family of these operators. Okay, so when t equals 1, it's the operator we looked at before, although again, in the previous case, we just looked at the self-dual and the anti-self-dual parts, but the coefficients are the same. So, so when t equals 1, well, all right, so when t equals 1, it's the same operator as before, but again, you're looking at the full curvature, so you're subtracting something a little bit more. So if you just check what that means on the level of eigenvalues, it turns out you decrease the eigenvalue because this is a negative term. So the eigenvalue of this operator, when nabla was a Yang-Mills connection, was non-positive, and I've just decreased it a little bit. So actually, the first eigenvalue of this operator, but it's just an inequality. I'm just using the fact that W plus is less than or equal to W. And all right, if you replace these with the pluses, I know that the eigenvalue is less than or equal to 0. So if I just, all I'm doing is increasing the potential here. So I push down the eigenvalue. OK, so I know when t equals 1, that eigenvalue is less than or equal to 0. When t equals 0, what do I know? Well, when t equals 0, I'm just dropping all of this. This is just the conformal Laplacian. All right, so its sign just corresponds with the sign of the Yamabe invariant. And I'm assuming the Yamabe invariant is positive. So this must be positive. So the conclusion is that there has to be a t0 somewhere between 0 and 1 such that this operator has a 0 eigenvalue. Just continuity on the parameter t. So that means if I look at this modification of the scalar curvature given by this, what is this, 2 root 6 w plus 3 gamma 1 f plus. So if I look at this modification of the scalar curvature, it implies that with respect to this metric, oh, sorry. All right, this is equal to 0. OK, so the lemma, sorry. So the lemma implies that if I compute this quantity, so I'm thinking and writing forward and backwards. I have a bad habit of that. OK, so all right, so the eigenvalue here is 0. And so that means that there exists a conformal metric for which the corresponding curvature quantity is 0. So there exists g tilde in the conformal class such that this modification of the scalar curvature that I just wrote is identically 0. OK. Anyway, the point is you make a conformal choice of metric, and now the scalar curvature is just equal to some multiple of the vial. No, that's not the plus. Some norm of the vial plus some norm of the curvature of the Yang-Mills connection. All right, that'll come in later, but anyway, it's a crucial part of the argument. OK, now let's go back to the second variation. OK, so remember that if you take the second variation of the Yang-Mills functional, so I vary the connection in this way. I take the second variation. I get 2 times, let me put a half over here to get rid of the 2. I get the inner product of the Jacobi operator acting on B, inner product on B. So that's the index form. So I want to look at the, write the index form out again. So if I write out the index form, so to remind you of the formula, so if you integrate that rough Laplacian term, you get this, all right, plus the Ricci tensor of the base acting on the 1 form, plus this bracket term. All right. Now, basically, OK, so I can view this as a Dirichlet form for some Schrodinger type operator, but the curvature terms I've got to estimate better, and I want to get it back in terms of the scalar curvature. So here's what you have to do. So I'm going to split this up into 2 terms. I'm going to split it up into a term that looks just like the Dirichlet form for that operator I wrote earlier, where the leading term was like minus the rough Laplacian plus 1/6 scalar. So I'm going to add a scalar curvature term here, and that means I'm going to have to subtract a scalar curvature term here. So now I have a Ricci minus 1/6 scalar acting on B plus, let me just write it this way, this inner product of this bracket term. So now what I want to do is just do some simple linear algebra estimates of this. Well, not so simple, actually. If you want to get decent constants, it's actually a fair amount of work. But I want to estimate all these terms. So if you do that, what you get is the let me put this in yellow. So I want to estimate all the garbage in yellow here. So the claim is that all this stuff in yellow is greater than or equal to, you have a very simple estimate, minus 3/4, let me call it z squared, I'll tell you what that is in a second, plus some other constant, I won't tell you, but it's explicit, times b squared. So this is just something involving the Ricci tensor acting on b. This is something involving the curvature of the connection acting on b. And this is more or less a sharp inequality involving these.
What is Z?
Okay, so z here is the trace-free Ricci tensor. All right, so this would be 0 if it were Einstein. And beta, I mean, I'm not going to bore you with what it is, but it's explicit. It just depends upon this constant gamma 1 and also T naught. So I mean, it's all explicit. So the conclusion is that this Dirichlet form for the index, you can write it as a Dirichlet form for this operator. This acting on B, inner product B, where V is just this collective junk there. So I'll call this V. So mine, right? Just I put a 1/6 scalar curvature term here. I have to subtract 1/6, and then all the curvature terms I collectively estimate this way, and just call that your potential. So here's a Schrodinger operator of the form that I can quote the estimate I erased, right, acting on B, inner product with B. And this Dirichlet form is less than or equal to this Dirichlet form, so if I'm counting negative eigenvalues, I'll reverse the inequalities there. So you apply this estimate for the number of negative eigenvalues. And what you get is a number of negative eigenvalues of your Jacobi operator. So this will be the index plus number of non-positive eigenvalues. So that include the index and the nullity, all right? And it's going to be less than or equal to some constant. So I won't write out the constant, all the dependence I did a couple minutes ago, but to remind you, it depended upon basically the Amabi invariant and the dimension of the structure group of the bundle. And then times the L2 norm squared of V, so V squared, where that's V. Okay. So V squared is 3/4 Z squared plus this constant that I'm suppressing times this. Okay, so this almost looks like the estimate in the conclusion of the theorem, right? So you have the index plus nullity is bounded by some constant times this integral. So there's your energy, but you're stuck with this, right? So what do you do with this? Yeah, so I should have said, so just like the, so we did this, we said that by this eigenvalue argument that there exists a metric for which the curvature, scalar curvature satisfies this condition. So what you do at the outset is you have your Yang-Mills connection, you compute its curvature, you do this conformal change to satisfy this condition, and that's the metric you work with from now on, okay? So this G tilde is actually the metric that's in play in all these estimates here, okay? It's conformal invariant, so it doesn't matter what metric I do with respect to, so I just do with respect to that one, and then run the argument, okay?
Why is that expression not squared?
Which one?
Yeah, because your V, is that the square there?
Did I forget to put a 1/2? I should have put a 1/2 here, sorry. This should have been a 1/2. Because in the curvature terms are linear. So this had to be linear. Yeah, thanks. Yeah. Okay, so this is the problematic term. And this is where the choice of conformal metric saves you. Right? So this is the last step. So what you now do, so you'll remember that the Euler characteristic shows up in the estimate. So what you do is you use the Chern-Gauss-Bonnet formula. And it turns out that one of the terms is the z squared. So if you just rewrite the Chern-Gauss-Bonnet formula, you can express 3/4 z squared. So what are the coefficients? It's minus 12 pi squared times the Euler characteristic plus 3/2 Weil squared plus 1/16 scalar curvature squared. All right, so what I do is, in this estimate, I take out the integral of z squared and replace it with these three terms. This is good, that's a topological invariant. This is good, it's a conformal invariant. Wait a minute, I got the scalar curvature term. But as I said a few minutes ago, at the outset, when you begin this process of doing these estimates, you do it with respect to the metric that satisfies this condition. So the scalar curvature already is in terms of the Weil tensor and the norm of the curvature. All right, so you stick that in. And so this term actually, I won't write it all out because that's why the coefficients are so lousy in the estimate. But this can be estimated in terms of W and the norm of the curvature of the connection. So that's why there was this weird cross term where you multiply the Weil tensor times the norm of the connection of the curvature of the connection, because you square this and you get this term times this term as a cross term. Okay? So that's the argument. So roll it back into here, and then that gives you the estimate of theorem B. Okay, so let me finish up here. It's going to be a long day, so I want to try to finish real quick here. I just want to say a few words. I'm not going to drag you through the proof and everything, but say a few words about applying the same idea to get an estimate on the index of Einstein metric.
Compare using harmonic coordinates to play the same role as the Coulomb gauge?
No. Well, no. I'll actually answer that question in just a second. So now, suppose I have a four-dimensional Einstein manifold, and with positive Einstein constant. All right, because the index estimate that we have relies on positive Yamabe, so I have to do this for positive Einstein metrics. Okay, so now, so Einstein metrics are critical points of the total scalar curvature functional. Maybe I shouldn't call it S. How about that's a pretty lousy S, but you get the idea. So it sends a metric to the normalized total scalar curvature. So you take the total scalar curvature and you take the volume and you put this power there. So you compute the first variation, you get the Einstein condition. Now, if you take a second variation, you learn that Einstein metrics are always saddle points in some sense. So the picture is like this. So here's your Einstein metric. So Einstein metrics minimize the total scalar curvature in conformal directions. So along this direction, that's the conformal class of G, right? But if you're perpendicular, if you're orthogonal to conformal transformations and orthogonal to trivial deformations, which are given by the action of the diffeomorphism group, so those are known as transverse traceless variations, right? So then you will maximize modulo a finite dimensional subspace. It's the dimension of that finite dimensional subspace that defines the index of an Einstein metric. Right? So index means the dimension of the space, so I write it as a maximum, but again, it's just maximum modulo finite dimensional subspace. So you asked about the Coulomb gauge. It's the transverse traceless condition is the gauge fixing condition here, because the diffeomorphism group is the gauge group. Yeah. So yeah. So in this case, we're index plus nullity. Nullity means it's going to be the kernel of the linearized operator. So those are infinitesimal Einstein deformations. So if you apply this, our index estimate, again, so I'm not going to go through this, but you cannot use the same, it's a different setup. It's a different Jacobi operator. You're going to have to make a different choice of conformal metric, but the strategy is the same. And you get the following corollary. And this is what I'll end on. So it says the estimate's kind of strange, but it makes perfect sense when you stare at it. I mean, the constants maybe don't make perfect sense, but the shape of the estimate. So this estimate is going to say that if you have large index, so in the Yang-Mills case, large index means you have a lot of directions where you can basically go up. So it should be pushing the energy up. Right? So big index, big energy. For Einstein, it should be the opposite direction. Big index means there's lots of directions to go down. Right? So big index should mean smaller energy, which should mean smaller total scalar curvature, and that's what this estimate says. So you get the following. So you have a topological term, it's the other characteristic, and then here you get 3 plus some constant here, I'll tell you it is in a second, the index plus the nullity of your Einstein metric. And so delta is just, again, this is where the E is hiding, so 1 over 24 E squared. So if the index and nullity are really large, right, this means that the Einstein constant has to be really small. Same spirit though. Okay, then I won't write anything, but let me just also say, there's work of Peter Lee in which, very similar in spirit. So then what he's doing, actually I'm isolating his result, but in fact, there are many results along these lines where you take a classical vanishing theorem that says, okay, under this curvature condition, this dimension of cohomology vanishes or something like this. Any kind of, pick your favorite vanishing result, right? And you weaken it to come up with an estimating theorem. So if you weaken the curvature condition, you don't get that say the space of one forms is trivial, but you get a bound in the dimension of say harmonic one forms, this kind of thing. So you go from a vanishing theorem to an estimating theorem is the term. So Peter Lee did that by looking at what it boils down to is kind of like index estimates if you look at it the right way for Hodge Laplacians. So these can also be applied using our index estimate, and you get, for example, 2 forms in 4 dimensions. Again, it's a conformally invariant condition, so it makes sense that your estimate on the space of harmonic 2 forms you should be able to estimate that in terms of conformal invariance, and we estimate it in terms of some L2 norm of the Weyl and the Yamabe invariant. All right, so the other, like if you look in this work I just referred to by Peter Lee, it depends upon things like the diameter and the Sobolev constant, geometric data that you're not going to get your hands on in general, and they don't again capture the conformal invariance of the condition. So, okay, I'll end there. Thank you very much.